Dear students, in this video, we're going to look at the perceptron learning. Last time we've looked at the composition of a perceptron, the simplest neural network that we can have with only a single neuron with many inputs, and the activation function as a hard limiter function to be the step or the sign function. And of course, we have the threshold as well to adjust during learning. And based on these inputs and the threshold and activation function, you can compute an output for what particular neuron. We're going to take some examples in this session, in this video, to how we can actually compute the output of perceptron. Now, what do you mean by perceptron learning? It means you have a given data set, you have a given training set, which have collected for your process, and output would have to be binary, because we see the perceptron uses the hard limiter function step or the sign function as activation function, so the output would have to be binary, but the input in this case we're going to use n and o, so we'll be having binary input variables, but there's no such requirement. Your inputs could be continuous. Okay, so in this video we're going to see how can a perceptron be made to learn its classification tasks. So in the previous examples we looked at the n and o, so we're going to use these particular training set to illustrate how do we train a neural network to replicate these two logical functions. And we've also seen that the perceptron could not represent an EXOR, but we're going to try today to make a perceptron learn the EXOR function and see what happens. But as we've seen in the previous session, since the EXOR function doesn't have a linearly separable boundary between the two classes, it should not be possible to replicate it to using a perceptron. Means you can't use a perceptron to learn the EXOR function, but we're going to see practically today why this is. Okay, now remember in the previous session what we did, we actually plotted, let's say we take the example of an n function, we plotted the two classes. So we had one instance of the inputs which gave class 1 and 3 instances of input which gave class 0, and then we could just draw a boundary between the two, and from the boundary we could see what weights do we need to use in the threshold. But in this session here, we are not going to use this approach, because in practice you're going to get training sets which have a much more than 2 inputs, for example, and you can't always just plot them on a scatter plot and draw a different boundary. So in this session, we'll see how to develop a systematic approach to learn the perceptron, where we can set initial random values for the weights of a perceptron and its threshold as well. And using the systematic approach, we're going to develop an algorithm to train the perceptron. So we're going to consider n and o logical operations as training sets. Now, initial weights are randomly assigned at first. So when you start the learning process, you're going to need an initial value for the weights and for the thresholds as well. And then based on that, now you're going to start making adjustments to these weights and threshold until you come to a stage where your neural network, your perceptron, is able to give as close as possible the outputs you expect. So we'll see what does that mean as we go along. The weights are updated to obtain the output consistent with the training example. Okay, so if you have, if you just go back and just look at any table of the boundary function, let's take the n function here. So your two inputs are x1, x2, and then you have an n here, which is the output you want. So in this case, we see when x1 and x2 are both 0, we expect to get an output of 0. Yep. So as a result of the learning process, if at the end of the training, you are able to arrive at the weights and threshold for your perceptron, which provides all these various outputs for a corresponding inputs, then you see how to train your network. Okay. But at any point in time, it means you have an output which you want, which is called desired output, and you would have an output which your neural network, your perceptron, is giving you, which you call the actual output. So the difference between the two, if you take the desired one minus the actual one, you get an error. Okay. So this is why we're referring here to an error. So the error that you get between your desired output, so y is the desired output and y is actual output, and the p here of iterative steps, because we're going to iterate through your training set several times to make small adjustments to your weights and to threshold. And so this p here stands for the iterations, the iteration number that you're at. So at any iteration step that you would have desired output and actual output which your network is giving to you, and the difference between the two would give error. And ideally, you want this error to become zero for all the training instances you have in the database in your training set. Okay, so here we are clearly showing here if we give x1 and x2 values here, which would be of course provided in your training example, and W1 and W2 would initially be randomly set as well as theta, and based on these values for any particular instance you have the training set, you are able to calculate an output YE, which your network is giving to you, and you would also have a YD, which would come from the training set. Now, what we're seeing here is what happens when this error that we've calculated here, EP, is actually negative or positive. So we'll come back to this in a few minutes in much more detail. So we'll be taking some examples, some combinations, which you would have to work out output, and then we'll be able to understand here what should we do when the error is positive or when the error is negative. But definitely when we look at this equation here, if your error was positive, it means your desired value is greater than your actual value. So you need to increase your actual value to make the error become zero. Similarly, if your error was negative, it means your actual value is greater than the desired value, and you need to reduce the actual value. This is what these statements are saying here. So we look at that in more detail as we go along. Now we look at this equation already. How do you calculate the weighted sum of inputs, XP, based on the number of inputs you have and the corresponding weights? So we've looked at that already. That's going to be a crucial step for us to work at. Every time we want to get output of a perceptron of a neuron, we need to find the weighted sum of inputs. So this could be the format of your training set. So this number here is simply instances that you have throughout your data set. So this is instance one. In this case here, say you have n inputs, so x1, x2, xn, and you have one output y. So for every instance that you're collecting information about your process, you would always have this n inputs having concrete values here. And for these particular combination of inputs, this is what you measured or what you want from your process. Similarly, now when you collect instance number 2 of the training set, you would have here a second set of inputs x1 to xn and the corresponding output. Let's take a simple example. If x1 here was temperature, x2 was pressure, let's say you had x3 which is flow and other inputs. So when you are now modeling or collecting information about your process, so x1 here would be the prevailing temperature, x2 would be the second input you want to model, and x3 we said, for example, x2 we say pressure, so you were going to measure pressure at this time, and let's say x3 was flow, so you would measure these inputs, and then for this combination of inputs, you would actually measure the output you process. Similarly, on the second instance, if the temperature has changed, the pressure has changed, the flow has changed, you would get a second input. And similarly, if you collect P instances of your inputs and the corresponding output, you get a training set, which is one way you could collect a training set. So to be able to train a neural network, you would need to have data, and these data are typically gathered from your process. So like you said here, the error, sign of error is fundamental for us to decide what do we do with our weights. Yep. So since any given input can positive or negative, these two inputs here, we said in this case, your x1, x2 here, we are assuming these could be negative as well and positive. So we are taking a broad, a general possibility here for your input. And the same way, your error can also be positive and negative. So we get 4 possible combinations for your input be positive, negative, and your error be positive and negative. So we want to see for these 4 possible combinations here, what would you want to do to your weights? For the time being, to start off, we're going to consider only the weights. We will not be considering theta, just to simplify the analysis initially. And then as we go along, we're going to see what do we need to do with theta as well. So let's consider these 4 combinations to find rules for modifying the neural network parameters, the weight and bias, to try to make the actual output match the desired output. So the aim here is to make these two become equal. So your actual value equal to your desired value, so that your error becomes close to 0 or 0 itself. Okay, to simplify that, like I said earlier, we're going to consider on the weights at this point. Yep. So we're going to consider only W1, W2. In this case, of course, this perceptron we are dealing with has only 2 inputs, but it could be more. It could be 3, 4, 5, 6, in above inputs. It matters, but each weight would have a corresponding, each input would have a corresponding weight that you want to see. Do we need to increase or decrease based on the value we're getting for YA, and YD would come from your trade. So let's start now with case 1. So we assume the following a training set. So this is the instance that you have your training set. Let's say x1 is 1, here x1 is 1, x2 is 0, and your desired value you want is the YD here is 1. So let's assume the W1 at this point is the initial value for W1 is 0.5 and your W2 is minus 0.3. We're given W1 and 0.3 here, assuming we're not dealing with theta again, so we are just ignoring theta at this point. So we assume theta to be 0 simply. So if you want to calculate now what actual value perceptron is giving to you, we are using a step activation function in this case. So we say step of, what did we say before? We need to find capital X, which is the weighted sum. So this is what we're doing here. We're taking 1 times 0.5 plus 0 times minus 0.3, so we get 0.5. Yep. So step of 0.5 is 1. Yep. So if your actual value now of your perceptron, the actual value of output is 0, and your desired value is also 1. So your desired value was 1 in your training set. Your actual value computed from your weights and your inputs is also 1. Then your error is 0. It means you don't need to do anything because your error is 0. You don't want to change anything. You're happy with what you're getting from your network. That's the trivial case. Now imagine now case 2. So what I'm doing here, I'm preserving the value of x1 and x2 as before, and preserving the weight W1 and W2. But simply now I'm saying for this combination of x1 and x2, I want a value of 0. And now imagine this particular training set you're using is not the N, is not the O, which is a trivial example we're considering on a case by case basis. Yeah, it's not a specific logical operation we're doing. So if I just go one slide back to exactly the same combinations here, except YD was 1 here, now I see YD has to be 0. So like we did earlier, the actual value you obtain from your inputs and the weights, you got a value of 1. So in this case, definitely you have an error, because the error that you calculate is always YD minus YA. So you get 0 minus 1, you get minus 1, so it's a negative value. So what particular combination are we dealing with here? We said our input that you are dealing with is positive, and the error which you're getting here is negative. Yeah, because we're getting negative error. So we are in this partial combination I put here. Now, what would we do in this case? You try to make YE become as close as possible to YD. This is the aim of learning, is to make this value of YE you're calculating as output of a perceptron become as close as possible to YD. So you can clearly see here when you calculate the error in this way, you find error to be negative. This simply means that the value of your actual output here is too high. You want to make it become lower, as you can see here. Error, and in negative error simply means YA is too high, you have to reduce it. How you reduce it is simply by, you have to modify the weights to try to reduce the value of YA. Now in this case, since your input is positive, you would reduce the weight itself. If you reduce the weight here for W1, which was 0.5, you start reducing this one, and you will of course reduce this one as well, because you apply the same rule for all the various inputs that you have. So in this case, if you want to make the error become closer to 0, you would have to reduce YA. In this case, you would reduce the weights to reduce YA. So let's take an example here. If we want to reduce the value of the weights, it is 0.5 here. If you bring it to minus 0.1, so we have reduced the weight, and this one was W2 was minus 0.3, bring it to minus 0.5. So if you calculate YA now with these new values of the weights, it's a step of minus 0.1 times 1, so minus 0.1. This one is 0, so 0 times minus 0.5, you didn't get the 0, so step of minus 0.1 is 0. Now the error is YD 0 minus YA 0. So it means we are validating that if your error was negative, okay, and your input was positive, you would need to reduce weights like we've done here, and it worked. Okay, so this is one rule we're getting. Simple. Now, case 3 now, we are setting x1 at 1, x2 at 1, the desired value is 0, and we are choosing different weights. So we say w1 is 0.1, w2 is minus 0.5. We follow the same steps here. We get actual value is step of 1 times 0.4 plus 1 times minus 0.5. So you get step of minus 0.1 to 0. So your desired value is 0, your actual value is 0, your error will be 0, so you don't need to adjust anything, and you don't need to calculate y again because you've not made any changes to your weight. So you're happy here, means you're not dealing with any requirements. Now, like we've done in the previous case, we'll change this value of yd here from 0 to 1. This is what we're doing here. Okay, so like we calculated before, your y is going to be step of same thing, 1 times 0.4 plus 1 times minus 0.5. So you get step of minus 0.1, which is 0. But as expected, now your error will be yd minus ya. So you get a value for error of 1, which is positive now. Yeah. So this part of combination of configuration of a perceptron is giving error which is positive. Now, a positive error simply means your actual value is too low. As confirmed here, the actual value is 0 and your desired value is 1. So you have to increase actual value. How do you increase actual value? Increase, in this case, is increase the weight. Now, why you increase the weight is because your inputs are positive. If your input was negative, you would actually reduce the weight, as we see later. So the particular combination that we are looking at here is your input are positive. Both inputs are positive here. It's fine. And your error also is positive. So we are dealing with positive input, positive error. So we get an increase in weight as we concluded. So this is going to increase weight. So let's just quickly cross check. We are saying we have to increase the weight. So let's increase the W1 to 0.6 and we're increasing W2. So since it's negative here, we have increased it to minus 0.3. So you calculate the actual value gain. So you take 1 times 0.6 plus 1 times minus 0.3, get step of 0.3 now, which is 1, and your desired value is 1, so you're happy your error is 0 now. So we are simply validating again that in this case you will increase the weight. So this is what we're saying for this particular combination here with input positive, error positive, we have to increase the weight. Now let's go for case 5 now. In this case here, we're choosing a negative input x1 minus 1, x2 is 1, so it's positive is 1, desired value is 0, w1 is 0.5, w2 is 0.3. So again, let's calculate your actual value of your perceptron step of minus 1 times 0.5, so minus 0.5 plus 1 times 0.3. So we get a step of minus 0.2 overall, so your weighted sum of inputs is minus 0.2. Again, we are assuming theta to be 0. So we get a step of minus 0.2, 0. So in this case, your actual value and your desired value are the same. So error is 0. You don't need to do anything because you're getting what you want from your perceptron. Now, in case 6, now we'll change this value to 1, as we've been doing before. So if you change the value to 1 here, your y is still 0 as per the previous calculation. But now your error that you're getting is always yd minus your y is. So we get a positive error. Now, positive error we've said before, because error is always yd minus I. If you get a positive error, it means y is not high enough. This is what we've concluded. Yep, so it means you have to increase. Yep, so you have to increase your y. So you modify the weights. You reduce the weight for negative input and increase that for positive input. Because taking weighted sum of the input with the weight, okay? If your input was negative and you want to increase the weighted sum x, you need to decrease that weight for the input which is negative. For the input which is positive, you would increase the weight. So it depends on the sign of input. So what cases are we considering here? Our error is definitely positive, so we are along this rule here. But in this case, we're finding we have two particular signs of the input. So this input x1 is negative, so we're dealing with this one, and your x2 is 1, so we're dealing with positive 1. But this particular combination, if you just go back here, we find we already said we have to increase. Indeed, this is what we see again for x2. We need to increase the weight to make y increase. But for x2 now, this is what we are analyzing the new case, the new combination. In case your error was positive and your input was negative, you will need to reduce weight. You won't increase it because overall you want capital X to increase YA. So for this particular combination here, you're going to reduce the weight. Let's just do a quick calculation again. We're saying for x1, because it's negative, we have to reduce this weight. So we brought it from 0.5 to 0.1, 0.2, sorry. For x2, it is positive. Yep, so we'll have to increase the weight, its corresponding weight. So it's increases from 0.3 to 0.5. So again, we've reduced the weight corresponding to the negative input, and we've increased the weight corresponding to the positive input. So this is what we've done, and let's calculate again now. So minus 1 times 0.2 plus 1 times 0.5. So what we get is step 0.3 or is 1, and it's matching now your desired the desired output. So you find the error becomes 0. So this is again confirming that for this part of the combinations here, we have to do as follows. So we've studied already 3 of these possibilities here. We have one last one. Let's look at case 7 here. So if you just run through the calculations again, so in this case, we are showing both inputs to be negative. So x1 is minus 1, x2 is minus 1. The corresponding weights are as follows: w1 minus 0.5 and w2.4, again taken as 0. So y with the step of minus 1 times minus 0.5, so you get 0.5, plus minus 1 times 0.4, we get minus 0.4. So step of 0.1 is 1. So in this case, both our actual output of the perceptron and the desired output are the same. So we get an error of 0. We're happy, we don't do any change. Now, as we've done before, we're going to change this yd here to become a 0. This is the last case we're looking at. So if we make that yd become 0, our ya was 1 as before. So if we calculate the error, we get 0 minus 1. So yd minus ya, that minus 1 is negative. So our error now is negative, and both inputs we found are actually negative. Now, let's first look at that error. If your error was negative, it means your y is too high. You will need to reduce your y. Okay. Let me repeat that again. If your error was negative, because your error is yd minus ya, for a negative error, it simply means y is too high. You have to reduce ya. Now, if your x1 and x2 are both negative, and you want to reduce ya, you have to increase the weights, because you're always taking the product of the input with this weight. If you want to reduce ya, it means you have to reduce capital X. Okay. And since ya is too high in this case, it means you have to increase the weights. This is what we're saying. Okay. So in this case, we have to increase the weight, and let's calculate again. So let's try to do that here. W1 was minus 0.5. We want to increase the weights. So we take it to minus 0.3. So in our case, W2 was actually positive. So increase the weight to 0.7. Let's calculate again. So minus 1 times minus 0.3, we get 0.3. Okay. And minus 1 times 0.7, we get minus 0.7. So step of minus 0.4 is 0 now. So we can find that now your y was actually 1. When you increase the weights for negative inputs, you're actually reducing the y. That's logical. So in this case, we find the error becomes 0. So if you put all these rules together now, we get this. So this one is showing all the different decisions we've taken throughout these 8 combinations. So, for example, when input was positive and error was positive, we said you have to increase. When the input was negative and the error was also negative, you had to increase. And for the other 2 combinations, we said you have to reduce weight. Okay, so these modifications, the weights can be readily implemented by simply taking the product of error and the input. Now, if I just go one slide ahead, with this formulation here, where you're taking the product of your input and your error here, was proposed by Rosenblatt in 1960 as a very effective way to train perceptron. And if I go one step back here, why we're saying you have to take the product of your input with error? It's very simple. When your input is positive and your error is positive, if you multiply positive and positive, you get an increase for the positive sign. If you take a negative sign, multiply by negative sign, you also get a positive sign. So these 2 here are simply saying, if we were to take the product of error with the input, the value we'll be getting is corresponding to the change you want to do in the weight. Similarly here, if your input was negative and your error was positive, we said reduce. So if you take a negative times a positive, you're going to get a negative sign, means you're reducing the weight. Similarly, if you take a positive input multiplied by a negative error, we get reduced. So we are simply summarizing all this analysis we've said by simply saying, if we take the product of error with input, we're going to get change 1. So this is what Rosenblatt has proposed. If we take the product of input and its error, We get this one. Now we multiply this by an alpha here, which is called the learning weight. So we're not just taking the product of XI and EP and making changes in the weights. We're saying we want this to be reduced by a given proportion here, which we call the learning weight alpha. Now, what this equation is simply saying here is, if you want to calculate a new weight for a given input, you take the previous weight and you add by that factor we just worked out. If you take the product of XI and EP, yep, you will get the change you want based on the table here. Yep. And of course, you are fractioning this by this learning rate here, so you're not making changes abruptly. Now, this term here, alpha XR, is called delta W because we're making a change in your weight. So this is what we're going to implement. So the perceptron learning rule is quite simple. It's alpha XE, which is proposed by Rosenblatt. So your learning rate alpha is going to be between 0 and 1. If you set the maximum at 1, means you're just taking out X times E here. The learning rate is typically modified adaptively in learning algorithms that you have in software like MATLAB or other AI platforms, but in our case, we're going to keep it fixed. Yep. So the way we're going to deal with the learning for the perceptron is going to be quite simplistic. In optimization routines that you have, this alpha rate would be actually changed adaptively during learning based on the error or the rate of change error have. Now, all this summary you find here is simply in the table there. So if you find this part, let's just take one of them. So if your error was positive, and your input was positive, you will need to increase because plus times plus is increase. Then in the same way, if you look at the three combinations here, you're going to conclude that for the product of the error times input you have, you get the change you want. So that's very well summarized what we've seen before. So this is what the perceptron learning rule does. So let's try to implement this perceptron learning rule now on the logical AND operation. So like we said, we're going to use the logical operations AND, OR, and EXOR as training set to illustrate very simply how a perceptron is trained. But like we said, also we can use real world data as well. Now, how does the training actually takes place? Let's spend some time on that. So in training a neural network, the training set is fed repeatedly to update the weights. So if you have 4 instances, so 4 combinations of input in your logical AND function for 2 inputs, you will feed these 4 inputs not just once, you feed it many times, because every time you feed it once, let's say one particular instance here, you will have a particular error. That error will be used to update your weights, but you can't just feed your training set only once, because you fed many times. The training set is fed repeatedly to update the weights. One training sequence in which the full training set is used to update the weight is called an epoch. So what's an epoch basically for the N logical function? When you fed all the 4 combinations of x1 and x2, this is called one epoch. When you feed it now, so it means one epoch in this case would be consisting of 4 iterations. The 5th iteration would already be the 2nd epoch. So 5th, 6th, 7th, and 8th would be part of the 2nd epoch. Now, when you feed the 9th one, it's going to be in the 3rd epoch. So this is what an epoch is. When you're fed the training set fully one time, and then you go in the 2nd epoch and 3rd epoch. Was just for the training sample of an AND operation. An epoch would consist of 4 training examples. I'll show in the next table here. So this would be our training set for the AND operation. So we've seen that before. So 0, 0, 0, 0, 1 is 0, 1, 0 is also 0, 1, 1 is 1. So this is going to be the first iteration, 2nd, 3rd, 4th. And this is going to be one epoch. And then at the end of this iteration here, you would go back and feed this one again. And then you want a 2nd epoch, and you will do that repeatedly until you get convergence. So we'll discuss as go along what is actually convergence. Now let's look at the steps you would use in training a perceptron. First, you would have to initialize your weights. So initially, you would have the architecture of a perceptron, which is one neuron, because we said perceptron is just one neuron, but the number of inputs that you're choosing would be decided, will be determined from your training set. If you have 10 inputs in your training set, you would have 10 inputs to perceptron. In our case here, you have 2 inputs, x1 and x2 only, and 1 output, because you know every neuron has only 1 output. But very important here is the number of inputs are. So you would set initial weights, typically in the range -0.5 to 0.5, but it can be outside this as well. And you would, of course, need a value for threshold theta here. Now, in this equation we've already determined, we know how to change the weights, but we've not yet discuss how to change the threshold. So we'll look at that later. Now, once you are able to set the initial values and the initial weight, it means you can straight away find a value for y like we've done in the 8 case we've done earlier. So if I give you values for W1, W2, up to Wn for all the inputs, and from a training set you have the values of these inputs, you can work out a y as follows here, and you're using a step activation function. Now, once you're able to find the actual value y8 means you can now correct, because from y8 you can work out error, and like we said before, you can correct for your weights using this equation. Now let's come back to the threshold theta. Now, like I said, you are able to correct the weights based on the analysis we've done before. Now, what about the threshold theta, the bias theta? So this is your expression which we have for calculating y based on the weighted sum of inputs, and then we subtract theta always. So we're just making one simple change here. We're saying this theta is just 1 times theta. So if we do a small change here, which may seem trivial, but what we're saying now, just like your weight was multiplied by input, so if we take that 1 times theta, we're saying now your input for a threshold is -1, and theta becomes a weight. So if you compare this expression here, x times wi and 1 times theta, we're saying now your input for a threshold becomes -1, and the weight becomes theta. So it means from here, if you compare this change that we had for the weight is alpha xe. So it's the change now for a threshold is going to be, this is your term here, correction. So it's a previous value of theta, and now it's a correction. Alpha, your x is always -1, like we said here, and your e is there. So if you just again compare this expression here for correcting for weight is alpha xe is alpha, your x is always -1 if you compare these two here, and then you will obtain for that perceptron. So this is why you're not considered in our analysis before, because now we are simply considering theta as a weight, and its input is -1. Okay, so when we apply, of course, the data on the perceptron, we're going to implement this. Now, once you have gone through one iteration, if I just go to the table again, so let's say we have fed this particular instance of your training set, and you've done this one, you make the correction. Now you go to the next step and again feed these ones and get a new error and correct your weights and use updated weights to implement this particular iteration, and at the end of it you get again an error, correct the weights, and you use updated weights for this particular iteration, and when you finish it, like I said, you go back here and you train again and again and again. This is what we're saying here. Once you have finished one iteration, you go back and you increase iteration by iteration number 1. So increase iteration p by 1 and repeat the process of activation and weight training until convergence is obtained. Now the question remains, what is convergence? When do we stop doing this iterative step of updating your weights and threshold? There are many ways you can do that, and one common way is to look at error, because for every iteration you're doing, you're getting an error, and over one epoch you can calculate a summation of error if you want for the whole training set, or you can look at individual errors. Now you could set conditions like that if you find the absolute error or the root mean square error over your whole epoch, and you set that when that value becomes below a certain threshold, in this case 0.001, or you can put a bit more accuracy, you want more a closer value of the actual value of your perceptron to your desired value. You can even decrease this further, but imagine the influence of this error here on your number of iterations. The lower this value, the more you need to iterate, and the higher the risk that you're overfitting a particular training set. So the issue of overfitting is, since you're using a particular training set to learn your neuron, but in practice you might have values which are not your training set. You don't want just your neural network to train to this particular subset of data you have of your process in your training set. So if you run too many iterations on your neural network, you tend to overfit. Means you tend to train your neural network to replicate only the data in the training set, and then when you actually feed values for your process in practice, it might not replicate well. So how we deal with this problem is, let's say in your training set you have, let's say you have 100 data, you have 1000 data. You don't use all your data sets to train your network. You use a subset of it, and you reserve a subset which is called a testing set to actually test your neural network afterwards. So in a way, we're saying don't test your neural network with data you use to train it. But you won't be doing it here because our training set is very small. Our training set is just of 4 instances, and all these 4 instances are unique in themselves. You have 0, 0, 0, 1, 1, 0, 1, 1. It means this is all we have in this case because of this example. But if you are collecting data with process, you won't have this limitation here. You're going to have a whole range of values. So from this, you can easily remove part of your training set to keep for testing purpose. But in our case here, since we're dealing with a very simple case of AND here, AND logical function or 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 EXOR, we'll need to use all of them, because all of them are fundamental in creating that logical function, and this is fully exhausted. You can't have any other combination outside this. Okay. So we've talked about convergence. It's basically to do with using an error metric to decide when to stop. You, as the designer of the neural network, you will need to set this value. Now let's try to implement these steps in learning on Excel, because in Excel we won't need any programming experience, so it's implementable by all of you here. We're going to use the Excel worksheet to implement these various steps for the N function, and we'll try the same worksheet for OR, and finally we can try the same worksheet for EXOR. Once you're set up the worksheets, it's very easy to just train the training set. Now, before we go to that, let's very quickly see how we can implement the various activation functions in Excel. You'll need that when you're trying to implement steps. We've seen these are the various mathematical formulations for our activation function for step, sign. So for the perceptron, we can use step or sign, which are hard limited functions. The sigmoid will be used later, and the linear, we said if ever you're attempting linear approximation, you'll be using it. Now, the difference between these expressions, the one we see earlier, is we have simply included the threshold theta. We know we have to subtract theta from here. So just shift to Excel now to very quickly see how we can program, we can implement these different activation functions, and then we will be using them in the steps later to train the perceptron. So let's shift to Excel now. Okay, so I'm just going to do this step very quickly. So let's say our input is changing from -10 to 10, let's say. Okay, now how can we implement the step function? Is using the if function in Excel. So if you have something like this, if. So what I've done before we start with this one, what I've done in this sheet here, if you go to name manager, I've already created a function, variable called theta, which I've set to 0 here. So later we can change this value to, let's say, positive value, negative value, and see the influence on your activation function. So here it is a value of 0. So how can you implement that step function? We're saying if. So this is your x here minus theta. So if this one is, if that difference here is greater than or equal to 0, so you have to put the value of 1, else it's 0. That's just the function. And if you just drag it down here, it's going to auto-populate. So just try to plot these two columns on a scatter plot. So this is a step activation function, which we implemented using the if function. As you can clearly see here, when your x minus theta is positive or equal to 0, it jumps to 1, and else it's a 0 on this side. Now, if you want to play around with the threshold theta, if I go again to name manager here, and if I just edit this value here, if we just make this value become 2, for example, you find that this has shifted, the graph has shifted on right, and now the threshold point becomes 2. This is how we are seeing a theta influence the activation function, just shifting the curve left or right. Okay, now the sign is very similar step. So you're going to take your x minus theta, and if that value is greater than or equal to 0, make it become 1, else if it's less than 0, it will become -1. So that's the only change that will be having as compared to step. Instead of the 0, we need to put a -1. You can see for sine is -1 and the change will be 1 here. So like we've done before, let's just quickly let's add it to the same graph. So let's add a new series here. We call it sine, and your x would be this one here, and your y is going to be these values, and this is now your sine activation function. Again, the threshold for changing between -1 and +1 is 2 because the theta was set at 2. Finally, let's try to program the sigmoid. Sigmoid, of course, if you look at the function that you have for it, is not a piecewise linear. It's just a simple mathematical expression. So it will equal to 1 divided by 1 plus exponential of minus, that was x minus theta. What's happening here? Yeah, so a small mistake, yes, plus, sorry, plus. Okay, so we get a small value and we just drop down. So let's add it to the same graph again. So select, add sigmoid now, equation function. The range of x is same, and your y is as follows. New values, and in this case we find your sigmoid in gray here. I'll zoom a bit. So this is what we get for the sigmoid, and you can find now the point here where it's transiting at 0.5 is actually 2. If I just change the value of one last operation here, if I just change the value for threshold theta to 0 back, just see the change that we get on your graph. So you can clearly see now everything has shifted back on 0. So now the threshold 0, it means the step is changing at 0, your sine is changing at 0, and your sigmoid is taking value 0.5 at 0. Okay. Now with this knowledge, now we can go on and replicate. So I'm just sharing back your PowerPoint slides. So we've seen how to implement this. Y is equal to x is very simple. We're just going to say y is equal to that particular value. But since you're not going to use y is equal to x, I will not actually program it. Okay, so now let's see how we can implement these various steps in Excel. So we'll be starting with initial values for W1, W2. Since we're replicating the n function, we're going to have values for x1, x1, its corresponding weight is going to be W1, we're going to set that 0.5, and x2, its corresponding weight is W2, we're going to set that -0.2, and the initial threshold is that 0.3. You can use different ways, different thresholds if you want. We're just randomly setting this. And once you have set these values, now we can work out an Excel sheet as follows. These are your epochs, these are your training set here. You can see clearly the training set is simply the n function. It's the first epoch. We have to copy this particular cell here many times down. We'll see that a few minutes in the worksheet. And this is all the initial weights we have set, 0.5 minus 0.2, and initial threshold for theta of 0.3. Now let's shift to the worksheet in Excel to try to implement this, and then to find the other columns here for y, the error, the final weight, the initial weight, and the threshold. And then once we find these final weights here, we have to transfer these weights here, because we use the final weights at the end of iteration of this iteration here. We use the weights that we have adjusted in the next iteration, and we keep doing this. So I'm going to now shift to Excel to show you how we do this. So I've created the same format we've just discussed here in this worksheet here, where you have your iterations here. I put many iterations till 100, corresponding to 25 box. Now inputs we've said as follows. So you have the first combination is 0, 0, and the corresponding output is 0. Then we have 0, 1, corresponding is 0. Then we said 1, 0, corresponding is 0 again. And the last combination for an AND operation will be 1. Okay, so if we sum to these, So this is your training set here, which we have to actually copy many times down. So we'll do that in a few minutes. Now the initial values we find for your W1 was 0.5. Okay, so this one is 0.5. We have selected this one to be -0.2, and we have selected this one to be 0.3. Okay, again, let's just send this. So 0.5 minus 0.2 and 0.3 Ts. Okay, now based on these initial values here we have for your initial weights and the threshold, we are able to work out YA, like I just said, using the if command to implement the step activation function. So you say if. Now, how do you calculate your capital X is by the product of X1 with W1 plus X2 multiplied by W2, so it's a weighted sum, minus the threshold theta, like we said before. So if this product here is greater than or equal to 0, then the value of Y is 1, else it's a 0. So this is how you have implemented the step activation function for YA. Let me repeat that again. So you have to take the weighted sum of your inputs. So you take X1 times its corresponding weight plus X2 times its corresponding weight minus threshold theta, here this one, and here you have an actual value of 0. Now, once you have an actual value, you can work out an error for that particular iteration. So your error is always desired value minus actual value. In this case, getting an error of 0, but because of course your YD and your YE are the same. Now, what do we do now to find your final weight is by taking the initial weight plus you need to have an alpha. Okay. Now, in the sheet, I've programmed already a variable called alpha. You have seen alpha is 0.2 here. I call it alpha. So it's alpha times x. Now, W1, the corresponding input is x1 times error e. Alpha x e. So we're taking alpha x times e plus the previous weight. The same step you're going to do for W2 is equal to, so the core value for W2 is found here, plus alpha times x. Of course, you use x2 because talking of W2 is corresponding weight. Alpha x is alpha times x times e. The error is both is common. The error that you're using for both weights is the same because it's 1 perceptron. So you get this value. In this case, you find your final weight and your initial weight are the same for the simple reason that your error is 0. But it will not be the case as with each weight. Now, for finding the new threshold, you said you take the old threshold, which is this one, plus alpha times x. We said x for a threshold is -1 times e. So this is what we're getting. Again, you find the threshold change because error is 0. Now, next step is once you've iterated, once you've done one iteration, you're going to use these weights now in the next iteration. So this is equal to this value is equal to, so this W2 is going to be used, and similarly, this threshold we use now. And if I just drag this up here and pull it down, that means we're able to compute here. And what I'm going to do next now, I'm going to take this whole row here and drag down, just iterating now, iterating. And what we're going to do now, we're going to copy this one block and just copy it for various other epochs because the training set is the same as we go along from epoch to epoch. Let's try it for 10 epochs, and then like we said, once you have programs, if I just click on this one is always taking the weight in the previous step, this one in the previous step, same thing, the weight from the previous step, and the threshold is taking the previous step, and then you're finding your YE from the current values you have to have, and then the error you get, and similarly you will correct this on alpha x as well. So this is well programmed here. You just have to drag this down, and it means you are iterating now. Now, if we just look at the column error here, if I just highlight it, so you find there are places where your error is non-zero, and for this particular instances, you find that you are actually correcting for your values of W1, W2. So in this case, let's say W1 here was 0.5, it became 0.3 because error is non-zero. Similarly, W2 was -0.2 here, it remained -0.2 because your x2 is 0. If you take this case here, where error is 1, you find your W1 here was 0.3, became 0.5, and it was W2 was minus 0.2, it became 0, and the threshold also changing. So we're implementing that product of input times error and fractioned by alpha. Now, if you look at the error, how it's changing, because it's a fundamental metric for us to decide when to stop iterating. If we see at this point it's not yet 0, but at some point, if you find from this point onwards, 4 onwards, error is consistently 0, it means the network has converged. Is this data here? We don't have the training set, but it means we can stop from here itself. From epoch 10 is enough for us to stop because error is already 0. So I would encourage you to go forward and program an Excel sheet like we've done here and try to implement the steps and see how it works for you. So let's go back to a PowerPoint slide. So this is what we've just done in the Excel worksheet. We're able to calculate YA error for a particular iteration step, and then corresponding correction in weights, and then transfers this weights down here, work against this when transfer. So this is one epoch, and then we've done that for many epochs. And this is epoch 1, 2, 3, 4, and learning with point 2. You can also play around with the learning rate if you want. This point to seem to be fine. So in this case, if you find error metric for the first 3 epoch, it did not actually converge yet. You are still getting a value of -1 here for the error. So if you continue on from epoch 4, like we saw, the error became consistently 0. So it means now the network has converged and you are able to replicate the end operation. Now, what does this mean? If students tend to get confused, what do you do next? So if you take the weights and the threshold at the result of your of learning the perceptron. If you find this one is 0.3, 0.2, 0.5, it's still the same here. It's not changing at all because your error is 0. So it means we are saying W1 of 0.3, W2 of 0.2, and a threshold of 0.5 would be good to replicate the end logical operation. Now, how this is working up, if we take this threshold now and we just plug them into the equation we've worked out before for the addition boundary, the addition boundary is W1x1 plus WX2 minus theta. So this is what it is here, 0.3x1 plus 0.2x2 minus 0.5 equals to 0. If you just do a bit of manipulation here, you make x2 become subject of formula, you get this equation, x2 is going to 2.5 minus 1.5x1. And if you plot that on the graph here, where you have your 3 0 classes and your 1 class, which is class 1 in your end logical operation, this is the equation of this line here, which we've just find out. So just here, it's not really here. You could have larges here, but based on the training we've just done, it is exactly on this class 1 here. If you plot in 3D, this is what you get. So this is what the activation function is doing. This is what the perceptron is doing for these 3 combinations you have here of your inputs. So 0, and you have 0, 0, you have 0, 1, and 1, 0. It is actually down here on the surface, which is at the level of 0. And then for the particle combination where you have 1, 1, which is here, it is shifting it up. So you can find this threshold here is exactly on the class 1. This is why you're finding it here. Yep. Now we've done that for the logical AND operation. You can do very simply now, just replace your training set in your sheet for this one now. So for x1, 0, x2, 0, you keep it at 0, but for the other 3 combinations, just replace once and you copy down and you just train it. You can use different initial weights for your W1, W2 if you want, and test again. And these are the results obtained. So very similar sheet here. And I'm just going to show you the results obtained. So like we said before, for an error for the first 3 epochs, we saw that we have a -1 here for one of a particular combination here. And then as we go for the 4th epoch, we find errors consistently 0, means the network has converged. Again, we're going to take these weights and threshold now, which will be different for the logical operation as compared to logical N. So if we do that now, we find W1 to be 0.5, W2 to be 0.2, and a threshold of 0.1. So if we again do the same exercise we've done before for the logical N, we try to create addition boundaries. So it's x1 times 0.5 plus x2 times 0.2 minus threshold. We always subtract the threshold like we see, minus 0.1, and it's a different boundary. And if you do a bit again of manipulation here, make x2 become subject of formula. we get this equation here, x to the power 5 minus 2 to the power 5 x1. And if we draw it in a graph now, we find that now we are separating the two classes. The class 0 is here and the three class 1s are here. This is where the decision boundary is found. And if we draw a graph now in 3D, we find this is what's happening. So this is a 3D plot of it, and this is like the top view of it, where you find the class 0s here, and these are the three class 1. This is what it is the perceptron is doing. Okay. Now earlier we've tried to when we were trying to discuss how perceptron works in terms of linear decision boundaries, we've concluded that the EXOR function cannot actually be implemented using perceptron. And let's try now on the sheet that you have, just replace. So in the sheet you have for the OR, just replace the last combination where x1 is 1 and x2 is 1 by 0. You have EXOR now. Make sure, of course, all your epochs have the same values. Strings are the same. So if you do that now, I'm just showing the results, so I would encourage you to try that. If you find the result we're getting here is an error, it's consistently not yet converged. You find the errors are not going to 0 consistently. So we are at 10th epoch here, and then till 20th epoch is still not consistently 0. You're considering this column here. If we go from epoch 21 to 30, still not converged to 0. And till epoch 40 as well, till epoch 50. If you keep running more iterations till 100, 1000, 10,000 epochs, you find this is still not converging. Simple reason, like we've explained before, the EXOR function doesn't have a linear boundary. So the perceptron will not be able to demarcate or to replicate the EXOR function. So I've just done a simple plot here of your error that you have, the error in the output against iteration step. You can see always your error are jumping back and forth. It's not converging to 0. If you plotted a similar graph like this for the AND and OR function, you'll find initially you do have some errors which are non-zero, and then it just flattens out to 0 in this case. So it is found that the network does not converge for the EXOR function. So this confirms the fact that a simple perceptron cannot represent the EXOR function, and in general, any data set where linear boundary cannot be drawn to separate classes cannot be solved by a perceptron. Now, to solve such high complexity problems means problems where you need a boundary which is non-linear. You would need more advanced neural network. One example of that is an MLP, a multi-layer perceptron with a hidden layer, like we've discussed earlier. And it took quite a while actually to come to the algorithm to train perceptron, to train a multi-layer perceptron. But ultimately, one method which was proposed by Brian and Ho in 1969, was the backpropagation method. You've seen in 1960, it was proposed by Rosenblatt, the Perceptron Learning rule, and it took almost 9 years. It was quite a lot of research efforts into training an MLP, a multi-layer perceptron, which was not that straightforward for the method to converge, because here we have more number of weights to adjust and we have more number of thresholds. But we have one fundamental problem in using the perceptron rule to train an MLP. Yep. So we're going to look at that next video. How do we actually go forward to train a multi-layer perceptron? Is going to be based more or less on the perceptron learning rule proposed by Rosenblatt, but with some fundamental changes. We'll discuss that in the next video. Thank you.